Okay, in this video I'm going to look at the matched pairs t-test. Frequently what we'll do with the matched pairs test is a pre-test, post-test, in which each person serves as his or her own control group. So this is just a one sample t-test. It's easier to see in the pre-test, post-test, it's the same person. But even when we're just doing, strictly speaking, matched pairs, we're still treating this as a one sample t-test, and we're getting one measure per person in the pre-test, post-test, or one measure for the matched pair when we're doing it in that case. So here we have a pre and a post-test, and we have scores in the pre-test of 14, 8, 11, 6, and 4, and in the post-test 19, 7, 13, 8, and 6. But what we really have is one sample. These are the same, call him Al, and this will be Barbara, and so on. So, but anyway, we have 5 people here, one sample of 5 people. Getting into the matched pair strictly, this could be Al and Alicia, 2 people that are alike on the characteristics that we think are important in terms of differences in this study. So what we're going to do now for each pair is just get the difference. In this case, you can subtract whichever direction you want. I'm going to subtract post minus pre, mainly so I can have positive numbers for each person. So 19 minus 14 is 5. 7 minus 8 is minus 1. 13 minus 11 is 2. And I'll leave the rest of that math to you. So I have those differences, and I'm just going to compute the mean of those differences. D bar is equal to the sum of those differences. So we took 5 minus 1, 2, 2, 2, and added those up, and we got 10 right here. And so we just have the sum of those divided by the number of them, and that's equal to 2. So we have a mean of the D's, our D bar, is equal to 2. Of course, in addition to that, we're going to compute the standard deviation of the D's. So we had our D bar is equal to 2. We're going to get the standard deviation of those by subtracting 2 from each D. So we're going to subtract 5 minus 2 is 3, minus 1 minus 2 is minus 3. Last 3, 2 minus 2 is 0. And then we're going to square those. 3 squared is 9, minus 3 squared is 9, and so on. And compute then the standard deviation of the D's. So we're just going to get the sum of the squared deviations divided by n minus 1. The sample size is 5. Again, this is just one sample of 5, n minus 1. And we end up with a standard deviation of 2.12. So once we've gotten the differences, remember we subtracted post-test minus pre-test, then we computed the mean of the differences and the standard deviation of the differences, and we had our hypotheses compared to 0. Now it's just a one sample t-test. So we're still going to have reject HO if the p-value is less than 0.05. We still have a t-test because we're looking at sample data. So instead of being x bar minus the mean of the hypothesized mean over s divided by the square root of n, now we have d bar minus the hypothesized mean of the differences. I could put an h there. Usually people just put mu d there. But if you want to indicate that it's hypothesized, I guess you can do that. Divided by standard error, which is the standard deviation of the d's of the differences, divided by the square root of n. 2 minus 0 over 2.12, the square root of 5, we have 2.11. That means that the value we have, this 2, is about 2.11 standard errors above the hypothesized mean of 0 here. So using our calculator, we can determine that a p-value is 0.051. And if I haven't done so yet, you might want to look one of my other videos. I show you how to do this on a calculator without using the TCDF function. But that'll work here as well. In fact, let me just tell you the 3 ways that you can do this. You can use the TCDF function. Remember second vars and get to the distribution, and you can put in lower, upper, and degrees of freedom, which in this case will be 4 degrees of freedom, because we had a sample size of 5, so subtract 1 from that. You can use stat tests t-test, in which case you'll just enter in 0 for the hypothesized mean, 2 for the sample mean, 5 for the sample size, and I forget what it is, but the standard deviation that we had in this problem. The other thing you can do, and I have a video on this that you probably should watch, it's probably the easiest thing to do, but it deserves its own separate video. But basically what you'll see is that I'll put the pre-test scores in list 1 of my calculator, stat, edit, and list 1. Put the post-test scores in list 2. Highlight the L3, just go up to the top of the thing there and do L2 minus L1, and that'll be in that'll create the differences, the D's that we had earlier in this problem, in list 3. And then when you use your calculator, you can go to stat, test, t-test, but then at the top you'll select input of data rather than statistics, and you'll just then have to tell it that your data are in list 3, and then the rest of it will just be like doing a regular t-test. Again, I have a separate video for that, and you should look at that, but that's just kind of a reminder and overview. So strictly speaking, we will fail to reject HO because 0.051 is not less than 0.05. And we'll fail to reject HO and conclude that the training doesn't, or that it might not work. We haven't, at least at the very least, we've been using our standard criterion, we can't be confident that it does work. Well, so I have another question down here about that, and that is, even though we fail to reject HO, strictly speaking, that's pretty darn close. I don't think with a sample size 5 and a p-value of 0.051, I'm going to throw out the notion that we have something that's effective here. In fact, if we compute effect size, d bar minus the mean of the d's over the standard deviation instead of over standard deviation divided by the square root of n that we had when we did the t-test, I'm going to get an effect size of 0.94, and that's bigger than the cutoff of point A. That's actually defined as a large effect size. It's not statistically significant, using 0.05 as the cutoff, but looking at this, it's a large effect. The reason it's not statistically significant, or at least one potential reason why it's not statistically significant, is that we just don't have a very large sample. I'm also going to compute the confidence interval here, statistic plus or minus confidence coefficient times standard error. I'm going to do a 90% confidence interval this time. And so I have 2 is my d bar. I have my sample standard deviation, square root of n. And so this 2.132, again, if you look on your t-table, under 90%, and go down the left-hand side until you get 4 degrees of freedom. Actually, I think it's the first column. When you get down to 4 degrees of freedom, you should see the number 2.132. If you haven't done so, please look at your t-table and verify that you can get that. At any rate, doing the math, we come to minus 0.021 to 4.021. That includes 0. Well, 0 is the same thing as saying there's no difference, there's no improvement. And so if it includes 0, we would conclude that there is no improvement. Again, we're pretty close here on the limit. With a sample of size 5, I'm certainly not ready to throw away my idea that this might be worth looking at or something that I'd want to consider. So there might not be any improvement. Again, that's strictly speaking